So evaluating simplifying difference quotient. It's a weird topic, especially when you look at the expressions that you see here and you're like, oh man, this is about to get ugly. It's like out of the frying pan into the fire kind of deal. But it's really not that bad. Honestly, that's kind of like the worst thing I could say. I just dropped an iPad. I'm dropping everything here. Because it looks awful, right? So there's really no way it could actually be as bad as it looks. So
No, it's definitely bad.
well, give it a chance. Give it a chance. So let me explain the theory behind it first. I'm going to draw a quick sketch. An arbitrary curve. All right. And I'm on that arbitrary curve, I'm going to establish some axes. All right. So the X and the Y axis. All right. This arbitrary curve we can assume is a function of some kind. So maybe it goes on forever, maybe it doesn't, maybe it's truncated, but I'm going to call it y equals f of x. All right, that's the notation that we use when we want to say that an equation is a function. All right, but it's like the equation is a function, but I'm not telling you what the equation is. All right, but the equation has this graph. What we're going to do is establish what are called bounds. Those bounds are restrictions on the graph. So I'm going to plot a vertical line. I'm going to make it dash though. There's no dash tool on this app, so I got to do it the old dash way. All right, so this is the vertical line x equals a. All right, it's just some vertical line. We don't know the value, we just know that it has a value. Okay. And we're going to do the same thing for an end value. And we're going to call that a b. Just want to get around to it anyway. All right, so this is an interval. Right, this is actually the only part of the graph that we care about. So if you wanted to, you could kind of disregard everything else. What I'm going to do is I'm just going to kind of shade it in a little bit, or just kind of darken it in. All right, this is the only part that we care about. Over the interval going from A to B. All right. Now, there exists a point on the graph at the intersection between my vertical lines and the function itself. All right, there's one point at A and one point at B. All right, so every point in space, all right, so in real space with dimensions, with two dimensions, all right, so x, y, the Cartesian plane, whatever you want to call it, the x, y axis, a graph, if you want to keep it simple. Every point is defined by its distance first from the y-axis, then its distance from the x-axis. Right? The way we find a coordinate is by starting at the origin, moving to the right some number of units. Go darker there. Moving to the right some number of units, and then moving up some number of units. Right? That's an x movement followed by a y movement. All right, so I'm taking you back to like elementary school now. All right, but it's that important. What people lose sight of is that x is the distance from the y-axis. So x is the distance from the y-axis. And y is the distance from the x-axis. All right. So we could call this point x comma y. We could call any point x comma y. Right. But we actually happen to know the x value here. The x value is a. Right. But let's just kind of follow along with the logic here. Any point in space so I'll say two-dimensional space. Can be defined by x comma y. All right. Now over here, I mentioned, so right here, where it says y equals f of x, I mentioned that y and f of x have the same value. All right. One form of that notation tells us that y is a function, but specifically, it is called f of x. So I could also write a coordinate as x comma f of x. Right? Any point in space defined by a function can be represented as x comma f of x. All right. So if I'm following that mode, I'm looking at this point and I'm saying, okay, x comma f of x, but x is a. We've stated that right here. So it's really a comma, and this is where compositions come into play, because I'm evaluating f of x for when x is equal to a, which is telling me that if I replace x with a value in one place, I got to replace it with a value with that same value everywhere. All right. So this point would be a comma f of a. All right. So we've just named a coordinate in general terms. So if I know what a is, I can figure out the coordinate on this graph. So I would need to know two pieces of information. I need to know the a value, and I'd also have to know what the function is. But then I can determine what the coordinates are on that graph. Right. The same would be true for b. Right. So over here we're looking at x being equal to b. So if we're following the mode of x comma f of x, if x is equal to b, so if I'm replacing the x with a b, then I'd also have to be replacing the x over here with a b. So b comma f of b. And it's also something to think about when you say, if the coordinates are defined as x comma f of the x value, so you read f of x as a function of x, right? It's a function of the x coordinate. So if x is a, if the x coordinate is a, then the y coordinate has to be a function of that a value, which is in the x coordinate. Right? So it's always going back to a function of whatever the x coordinate is. So if I put a smiley face here, if this were a smiley face, the y value would be f of that smiley face. It's always whatever is here goes here. That's how coordinates are defined for functions anyway, in two-dimensional space. So I mean, there are limitations to it, but that's the idea. All right. So now, okay, well, we have this information. That's wonderful. What on earth are we going to do with it? Well, if you have two coordinates, you can do a bunch of things, not the least of which is write the equation of a line, find slopes. In this case, a difference quotient is what's called the slope of the secant line. All right. The difference quotient is the slope of the secant line, secant, connecting 2 points on some function f of x. Right? Secant is a geometric term. If you define it in a way that's useful for our purposes, it's really just a line that intersects a curve in 2 different locations. But in geometry, it's more, it has more to do with circles. But when you get into more advanced math, you realize everything could be thought of as a circle, which is kind of weird, even lines. So and it's kind of crazy, but a line can be defined as part of the circumference of a circle whose radius is infinity. Right? If you could ever get the radius of a circle out to infinity, all of the circumferences would become perfectly linear. Right? And very strange and mind-bending, and also very fourth dimensional, but it's kind of cool. So anyway, slope. That's the key word here. Change in y over change in x. So I have 2 sets of coordinates. I have a comma f of a and b comma f of b. If I draw a line segment connecting these 2 points, I could find the slope of that line segment by finding change in y over change in x. All right. So I'm gonna subtract my y values. One of them is f of b. The other is f of a. Then I'm going to subtract my x values in the same order. So my x values are a and b, but I'll subtract using the b value first, b minus a. So that's actually a difference quotient. Now, it doesn't look like this formula. I'll get to that in a second. But this is a variation of a difference quotient. It's a general rule for finding the slope of a line segment connecting any 2 points on a curve.
So A and f of A act like x and y?
Exactamundo.
Oh, that's so weird.
Yeah.
So they don't correlate. They're actually 2 different points.
Correct. Correct.
Oh man, I think my mind just got like mushy.
Just wait.
Same. Oh gosh.
I have been looking at that as though they are connected in one sequence. They are not.
No, the A gives the f of A, but then separate from that, the B gives the f of B.
So A and B are separate, and f of A and f of B are separate, and they're all separate from each other. Everybody's different.
Right, because one is an x coordinate and the other is a y coordinate, and they're both part of different coordinates.
Oh my God. Oh my God, go slow. Go slow.
So A and f of A are x and y coordinates. B and f of B are x and y coordinates, but from different points. So A is different from B because it's not at the same location. F of A is different from A because it's a y value instead of an x value. Just
Okay,
like F of
I
B
gathered
and B.
that. But what do we use this in real life for?
So this is the foundation of calculus, which gives us average rates of change and by extension, instantaneous rates of change. So an easy connection would be if you're driving your car and you look at the speedometer, that would be an instantaneous rate of change. But if you were to take the amount of time it took you to drive to work and the distance to drive to work, divide the two, distance divided by time, that would give you the average rate of change. That's an extension of this topic. Okay. So if we want averages over an extended period of time, this, in terms of a rate of change, this would be very helpful. So the thing is, if you think about like the stock market, right? I'm not going to pull it up, but if you were to pull up a graph just a trend graph of a particular stock over time, you see a lot of volatility, right? But if you want to get an idea of what's happening, what you can do is define a function based on some point over here and some point over here, connect the two, and find the rate of change. Now, that rate of change is going to have what we call a margin of error. It's going to have some deviations from it. We start getting into a little bit more with statistics there, but you'll have a sense of the trend. You'll get an idea of what the balance point is between the high and the low for that particular stock. Now, that's a linear case. What happens if you have something that's really volatile, right? So you have something that shows some fluctuations, something like that. Yeah, you can model it with a linear case, but you might be way off in some instances. You might be pretty close in some other instances, but you're going to be really off. Like you're going to think that the stock will be valued at this amount when really it's going to hit this amount. And if you sell it, you're going to lose a lot of money, right? So what we would want to do is use a different type of function. Maybe it's a curve function. Right. So if that curve function, maybe it's a perfect fit. I doubt it, but maybe it's something that's got some of the overall characteristics where maybe it'll be something like this. And you want to get a sense of the overall trend over small intervals. So you'd say, all right, well, let me get the rate of change from here to here, the rate of change from here to here, the rate of change from here to here. Those line segments. And the value in that is immeasurable because, you start getting into business terms and stuff like that. For more information, take my business calculus class. I don't always teach it, so it's not necessarily a thing. But if you know that there are going to be peaks and valleys in a stock, knowing what the rate of change is on average. So if I could find the slope here, here, and here, I'll have an idea of what the rate of growth will be when it's on the upswing. So then if I can just predict when it's going to hit the upswing, then I'll have an idea of how much money I stand to make and over how long, right? It's hard to believe that there's actually like this one basic idea leads to that whole world of analysis, but it's huge.
So this is an algorithm, in other words, like it's sort of like an algorithm to help you, like for instance, I have stock in crypto. Like if I did this mathematics for crypto, I can somehow predict how high crypto will go based on how low it is.
Yeah.
Or in the upswing. That's mind-boggling.
But you have to first notice a trend. You have to recognize that it's a cyclical trend. And then you have to apply the appropriate function modeling technique, which we're going to get to in this course. And then once you do that, then you apply a technique like this. I don't know why I hit an eraser. That was just ridiculous. A technique like this to help you get a sense of what the rates of change would be.
Awesome.
But it's really cool. The thing is, most of the time in a class like this, you never really get to do anything with that. That's why I do the tech assignments and discussions and stuff like that. And the hope is to try to build off of this. Yeah. So you'll find also, aside from the nitty gritty of just running the numbers and all that stuff, you'll find that maybe you're not interested in stock, but you're interested in something else where you can look at it and say, yeah, I don't care about stock, but I do care about this, which also involves rates of change. Let me see if I can use this technique for something like that. It's once you see it, you can't unsee it. All right. So there's another variation of this formula. You can see it right here. Let me just show you where that one came from. It's not like we have to do the whole thing all over again, but I am going to go back to the diagram and kind of play the what if game. So we're looking at, again, the 2 points. Let's go with this vibrant blue for those students who are at home. So let's say you wanted to just use this coordinate or this set of coordinates, a comma f of a. We didn't have some point b, but we did know some horizontal distance. So it didn't say, so this b stuff isn't here. They say instead that you're going to start at a and go h units to the right. All right. So if you do that, then your second coordinate, your second pair of coordinates would have an x value that increased, or your x value would increase from a to a plus h. All right. So alternatively, my power just blinked there for a second. We could say a plus h as our x value. And we know that the y value is f of whatever your x value is. So the y value would be f of a plus h. So it's possible to call it this instead of the b comma f of b. All right. Now, why the two different ways? Well, one way leads very nicely into the concept of derivatives. The other way, not quite as nicely. All right. But if I were going to take my blue stuff and find a slope, it would be f of a plus h minus f of a over a plus h minus a. And then on the bottom, you have a and negative a, so they'd cancel away. So you'd have f of a plus h minus f of a all over h. All right. So you look at that and you say that that's pretty close to this, except we have x's instead of a's that I have in blue. All right. So the difference here is this is the difference quotient for the slope of the secant line. So again, we never want to lose sight of that. Slope of the secant line connecting 2 points on f of x. This one starts at a and goes h units to the right. This one starts at a and goes to b. All right. So what we have here, this one is different from this in the sense that this one allows you to start anywhere you want. All right. So it's not just a fixed point on the graph, it's a variable point. Right. So this one allows you to start anywhere. Starts at any value of x and goes h units to the right. All right, the plus h would be to the right. However, it is possible for h itself to be a negative, but we always assume that it's going to the right symbolically. All right. So that's the theory behind it. And there's a lot of theory. There's a lot to digest there. You know, if this were a Khan Academy video, I'm sure he would say something like, all right, now stop the video and think about this for the next 24 hours before you move on. But we don't have that luxury. What I'm going to do is dive into an example, show you how it all works, show you the calculator that I created for you, just to kind of make things a little bit easier. And then we'll go from there. And then you'll have 48 hours to digest all this. All right. So you have a function here. I'm going to get rid of all this stuff here. Let me just open a new calculator. So f of x is equal to x squared plus 3x plus 7. They're first telling us to find f of x plus h, right? So this is notation. This is a composition of functions right here, the f of x plus h. It's actually, it ties in beautifully with what we did on the previous page, but after what I just showed you here, what we did on the previous page might feel like a lifetime ago, right? So what this is saying is replace all x's in f of x with the expression, with, does not have an e at the end, with the expression x plus h. All right, that's what that command is telling you to do. All right. So I'm going to rewrite my original function f of x. Everywhere I see an x, now there's an x in multiple places here. Everywhere I see an x, I'm going to replace it with an x plus h. All right, so I'm going to pop in an x plus h everywhere I have an x. And then we're going to simplify that. All right, that's the least exciting part about this whole process. Just kind of cleaning it up a little bit. So we have to use double distributing or the FOIL method, whatever you learn to call it. So I have an x plus h squared. So I'm going to write that as x plus h times x plus h. We're going to distribute that out. X times x, x squared, x times h, positive xh, h times x, well, it's commutative, so I could write it as hx or xh. I'm going to write it as xh, just so I can accentuate the like term part of this, like terms. And then h times h, positive h squared. We have an assumed 1 in front of each of those like terms, the xh. I'm going to put a 1 here and here. Combine those like terms. We're going to get 2xh. Bring everything else along for the ride. We also want to distribute the 3 here. So I'm going to bring the 3 through. So 3 times x, 3x. 3 times h, 3h. And then the 7 also comes along for the ride. If there are any other like terms, you would combine them, but there aren't any, so we would leave it like this. All right, this is pretty hideous, but it's correct.
Professor, I'm sorry to cut you off. You kind of lost me where you got the 3h.
The 3, oh, okay. So when I distribute through with the 3 times x gives me the 3x. 3 times the h gives me the 3h.
Oh, I'm sorry. I see it now. I'm sorry.
No problem. Okay. So for part B, we're actually going to use our answer for part A. It looks like B would be the harder part, but we just finished the harder part. The harder part is over, and it was hard. Don't get me wrong; it was definitely tricky, but that was the hard part. Now that we're done with this, we're in the home stretch, all right? So what we're going to do is take this difference quotient, f of x plus h. So f of x plus h minus f of x all over h, and make some substitutions. All right. First thing I notice x squared, oh, that's too big of a box. X squared plus 3x plus 7. That's what f of x is equal to. They told us that right in the beginning. So we know that. So we're able to substitute f of x out and replace it with its true expression. We just figured out what f of x plus h was. And that's this one over here. The only thing we won't know is what h is, but that's okay, because we're going to get an answer in symbolic form. I guess that's fine. I kind of want to. So we're going to make that substitution, and we're going to make that substitution. So I'm going to replace f of x plus h with its expansion, x squared plus 2xh plus h squared plus 3x plus 3h plus 7. Then I'm going to subtract from that f of x, which is x squared. I'm subtracting the whole expression. So parentheses goes around the x squared plus 3x plus 7. All over h. So once we simplify this, and there really isn't much to simplify, because we only have a few like terms, they'll cancel each other out, and that'll be the end of it. But once we simplify this, then we're done, right? Although I will admit, when you look at this, you say, oh, easy for you to say, this looks like it's terrible. But it's actually pretty easy, because all we're going to do is distribute the -1, right? We have an understood -1 here. That's getting run through. Justice League. All right, so minus x squared minus 3x minus 7. Now you see here, use my highlighter, I got an x squared and a negative x squared. I got a 3x and a negative 3x. And I got a 7 and a negative 7. Oh, Wonder Woman. So cancel them. Simplify further. We're looking at 2xh plus h squared. Oh wait, I overdid it. That 3h is still there. So 2xh plus h squared plus 3h all over h. We have a common h on the top. Okay. We'll check the chat in a sec. We have a common h on the top, so I'm going to factor that out. I'm going to factor out a GCF. So I'm going to divide each one of these terms by h. Right? See, I have an h here. I can take one of these h's and I can take one of those. Right? So 2x plus h plus 3. Cancel the common h. And we have it. 2x plus h plus 3. Right? And so that would be our final answer. Right? It takes a while to get there, but it does clean up pretty nicely. Exactamundo, 2x plus h plus 3. Okay. So I know you're dying to do another one, so we will, especially after all that. But it's a lengthy process. You don't need me to tell you that. You just see it. But it's very procedural. So it's a process that if you follow the process correctly, you'll get it right every time. there are plenty of instances in math where you can follow the process correct every single time and still, get it wrong. Those aren't very thrilling, right? So again, let me just kind of steal this. We're going back to this idea here that we're replacing all of the x values in f of x with the expression x plus h. That's going to be our first move. So rewrite the function. But instead of an x, we're going to replace all the x's with x plus h. So I'm going to rewrite the function, replacing every x with an x plus h. All right. Now, one good outcome is that you're going to see this x plus h squared pretty frequently. X plus h squared is the same x plus h squared from the last problem. So we've already done that work. You do it once and you're good to go. So all this is true over here as well, right? So you don't have to worry about doing that a second time. You can just steal your answer from the previous problem, right? So this would be equals, we still have the 3 there, but instead of the x plus h, I'm going to put, I'm sorry, the x plus h squared, I'm going to put this. And we'll go to the lighter color here. Kind of not very appealing, but it's okay. These two are equivalent, right? We still need the -2. But now I can just distribute my 3. And I'll have 3x squared plus 6xh plus 3h squared minus 2. Right, so that's what f of x plus h is equivalent to, right? So this is the same as this. So looking back at my difference quotient, f of x plus h, I already have that. I'm going to snag this. So this is this. I'm going to subtract from that f of x, put the whole thing over h, and then simplify. Get a different color highlighter here. I'm going to go with an orange, a variation of orange. So this is what f of x is. F of x is the 3x plus 2. So I'm going to put in a 3x, I'm sorry, -2 squared. And now I just have to simplify this. And once I do that, I'll have my answer. So 3x squared plus 6xh plus 3h squared minus 2. Again, that understood -1 is going through. So -1 times 3x squared, -3x squared plus 2 all over h. Like terms, look for them and cancel them if possible. Possible, that would be the word of the day. Possible. So 6xh plus 3h squared over h. See, we have a common factor on the top of h, so we'll pull that out. The 6x plus 3h would remain after you factor it out. And then the h's cancel, leaving you with just the 6x plus 3h. So it is kind of surprising that it cleans up so nicely when it starts off in such a mess. I mean, you're always going to have an answer that involves an X and or an H. So, you know, you come to grips with that, you're fine. But it should clean up fairly nicely. And if it doesn't, you start wondering, okay, where did I go wrong? All right. Now, part C here is new. You see that that's a variation on this formula, the f of b minus f of a. So it's a slight difference. It's just allowing us to work with all values of x rather than a particular endpoint, right? So we'll start off at point A, but we go off to wherever we want with some variable coordinate, a moving coordinate. Computationally, it's actually easier to set up than parts A and B, but it does involve some factoring. And so if you're a little iffy on your factoring, you might want to brush up in that area. But its setup is a lot easier. So if you have a choice in the matter, you're probably going to choose this this variation. All right, let me just move this over a little bit. So first part, we see f of x. We know what f of x is. That was given to us. 3x squared minus 2. All right, that's this expression right here. The second part says f of a. All right, so let me rewrite f of x over here. F of x is equal to 3x squared minus 2. F of a is a composition when x and a are equivalent to one another. So all this is telling me to do is replace every x with an a. All right, so you see I have an x here and an x here. I want to replace those with a's. So this expression here is what f of a would be equivalent to. So I'm going to make my substitutions now. Right? So I'm going to replace f of x with this, and I'm going to replace f of a with this. So 3x squared minus 2, then minus 3a squared minus 2. And the x minus a on the bottom stays put. There's nothing to substitute in there. So then, you know, it's easy to say this, but it's just algebra from here on out. We just need to simplify it. Right? So what I'm going to do is run through, we got, again, the understood -1. (3x squared minus 2 minus 3a squared plus 2 over x minus a. And cancel out the -2 and the +2. Doesn't seem like much, but it actually is pretty significant that we're able to do that, because I'll be left with 3x squared minus 3a squared over x minus a. We have a GCF up top. We can factor out a 3. But then what remains is actually factorable. So that 3 is going to be there in our final answer, but the x squared minus a squared factors to x minus a. If the difference of perfect squares, x minus a, x plus a. All right, that old technique, difference of perfect squares. You just Like if you had, for example, x squared minus 4, you take the square root of this guy, take the square root of this one, and just make the signs different. All right, so that's what we're doing here. X squared minus a squared. Take the square root of this one, take the square root of this one, and just make sure your signs are different. All right, so that's your crash course on difference of perfect squares. But we have a common x minus a that can be canceled. And so we're at our final answer of 3 parentheses x plus a. So 3 parentheses x plus a would be your final answer. Right? Now that looks very different from what we had on the previous or the previous part, because the other one was 6x plus 3h, but they actually both do the same job. They both will give you the slope of the secant line. And it's very easy to forget that that's what this is all about, finding the slope connecting 2 points on a graph. I got caught between curve and graph there. So if I know the x value of interest and the a value of interest, I can figure out the slope. Right? So it's pretty useful when it comes to that, but also it's going to help you understand the concept called the derivative when you get to calculus. But let me take a second and show you the Desmos I created. It's all, again, it's in the calculator link on Blackboard. But if you open the file, there's a bunch of things going on. I just wanted to walk you through it. So I used the first example here just to kind of get the bearings, but I'll actually change it. I'll just leave it at this. All right. So this is a point-based approach. So the first thing is points and lines, because if you're looking for a difference quotient, you're probably looking for it over a defined interval. All right. So over some interval from a to b, where a is known as a particular value, and so is b. All right. So I have this parabola here, x squared plus 3x plus 7. Depending on where I slide my slider, it'll position a at a different location. All right. So what we're looking for is the slope connecting any 2 points. All right. And so if we go down, I'll move this over here. If we go down, we have our 2 difference quotients, the f of b minus f of a over b minus a. That tells me that where I have my points positioned would give us a slope of 0. All right. And then I also have the f of a plus h minus f of a over h, also giving you a result of 0. All right. So let me show you what this would look like. I don't have enough space to do it. You know what I'll do is I'm going to throw in a separate page here, just so I have the room, and then I'll put it all together later. All right. So let me show you what the slope would look like if we took this example. I'm just going to do a screenshot here. But we did it over a defined interval. Big screenshot. Okay. Oh, that's weird. All right, so let's say, for example, we needed to find the slope of the secant for the function f of x is equal to 3x squared minus 2 from a equals 1 to a equals 3. All right. Oh, a equals 3. Sorry, b equals 3. All right. So there's 2 ways that we could go about doing this, we could use the lengthier difference quotient, or we could use the simpler, more user-friendly one. All right. So in either case, we computed the slope The slope is either 6x plus 3h or 3x plus a. Right? So what we would be doing is first establishing what the x value is in each case. All right? So in this case, this is our starting point. So we would let x equal the a value, which in this case is equal to 1. All right. H would be the difference between a and b, but that, I mean, I could write that, but the calculator is going to handle that. All right, I'll write it anyway. So h is always the difference between a and b. So 3 minus 1 would be 2. So if I needed to compute the slope here, it would be 6 parentheses 1 plus 3 parentheses 2. So 6 plus 6 would be equal to 12. All right, so that's one way to go about it. The other way to go about it, and again, it's all assuming that you did all this work algebraically, but this x value has a different role in this story. This x value is the ending point of the secant line. All right. So we know what a is, but in this case, we're going to let the x value be equal to b. So let x equal b, which in this case is 3. All right. So 3 parentheses 3 plus the a value is given as 1. 3 times 4 would be equal to 12. So in both cases, you get 12. So let me show you how the calculator would do it. So we start off typing in the original function. So 3x squared minus 2. Take a look at the picture. You can pinch zoom any way you want. Place the a and b values appropriately. So I put the a here at 1. The b value goes to 3. As long as you can kind of see it on the graph, you can feel pretty comfortable that you're in the right neighborhood. Once you do that, all you have to do is scroll down. F of b minus f of a over b minus a. That's this computation. Gives you a 12. F of a plus h minus f of a over h. That's this computation, also 12. Right, so it'll do the numbers, it'll do the computations for you, right? So the benefit of something like this is on the test, there's going to be multiple choice questions, there's going to be short answer. There's going to be instances where you need to show your work, and there's going to be instances where you don't need to show your work. If you don't have to show your work for a question like this, put it in the calculator and call it a day. If you do have to show your work, then unfortunately you're on the hook for this whole process, but that's sometimes unavoidable. Right. So let me stop the recording.